In a typical electrical distribution system, a transformer on a utility pole reduces high-voltage electricity to a lower voltage for use in homes and businesses. The transformer usually has 3 secondary windings, 2 hot wires, and a neutral wire. The neutral wire is connected to the grounding system at the transformer. This is accomplished by connecting the neutral wire to a grounding rod driven into the earth. Grounding the neutral helps ensure that the voltage between the hot wires and the ground remains balanced. Without proper grounding, voltage imbalances can occur, potentially leading to safety hazards or equipment damage. As the load in the electrical system changes, the current flowing through the neutral wire also changes. Grounding the neutral allows this current to flow safely back to the transformer, maintaining a balanced voltage between the hot wires and the ground. Grounding the neutral provides a low-resistance path for any electrical fault currents. This protects people and equipment from electric shock. Voltage imbalances can reduce the lifespan of electrical appliances and equipment. Grounding the neutral helps prevent these imbalances, therefore, prolonging the life of devices. The neutral wire and ground wire are not the same. The neutral wire carries current during normal operation, while the ground wire only carries current in the event of a fault. In some older electrical systems, the neutral wire might not be properly grounded. It is crucial to have a qualified electrician inspect the electrical system to ensure it meets current safety standards. Proper grounding is essential for the safe and efficient operation of electrical systems. Voltage imbalances can cause a variety of problems in electrical systems, including overheating, reduced efficiency, and equipment failure. Grounding the neutral helps to mitigate these issues by providing a stable reference point for the voltage. The earth itself serves as a conductor, allowing current to flow back to the source. This is why the grounding rod is driven into the earth, providing a direct connection to this conductive path. When a fault occurs, such as a short circuit, the ground wire provides a low impedance path for the fault current to flow back to the source. This high current flow causes the circuit breaker or fuse to trip, disconnecting the power and preventing electrical shock or fire. Without a proper ground connection, the fault current may not be sufficient to trip the breaker, leading to a dangerous situation. Grounding also helps to reduce electrical noise and interference in electrical systems. This can improve the performance of sensitive electronic equipment and prevent data corruption. Electrical noise can be generated by a variety of sources, including motors, fluorescent lights, and electronic devices. A properly grounded system provides a path for this noise to dissipate, reducing its impact on the electrical system. The National Electrical Code, or NEC, provides detailed requirements for grounding electrical systems. These requirements are designed to ensure the safety and reliability of electrical installations. It is important to consult the NEC and follow all applicable requirements when installing or modifying an electrical system. Some common grounding practices include bonding all metal enclosures and equipment to the grounding system, using appropriately sized grounding conductors, and ensuring that the grounding electrode system is properly installed and maintained. Bonding ensures that all metal parts are at the same electrical potential, reducing the risk of electric shock. The size of the grounding conductor must be sufficient to carry the maximum fault current that could occur in the system. The grounding electrode system typically consists of a grounding rod, a metal water pipe, or a concrete encased electrode. The grounding electrode system should be located as close as possible to the service entrance and should be properly connected to the grounding conductor. Regular inspections and maintenance of the grounding system are essential to ensure its continued effectiveness. Grounding connections can corrode over time, reducing their conductivity. It is important to periodically inspect the grounding connections and clean or replace them as needed. The grounding electrode system should also be inspected to ensure that it is still in good condition and that it is properly connected to the earth. In addition to grounding the neutral at the transformer, it is also important to ground the neutral at the service entrance of each building. This provides an additional level of protection against voltage imbalances and electrical faults. The service entrance is the point where the electrical service enters the building. The neutral conductor is connected to a grounding electrode system at this point. This grounding electrode system is typically connected to a metal water pipe or a grounding rod. The NEC specifies the requirements for grounding the neutral at the service entrance. These requirements are designed to ensure that the grounding system is effective in protecting people and property from electrical hazards. In addition to grounding the neutral, it is also important to properly ground all electrical equipment. This includes appliances, lighting fixtures, and other electrical devices. Grounding electrical equipment helps to protect against electric shock in the event of a fault. When an electrical fault occurs, the fault current will flow through the grounding conductor back to the source. This will cause the circuit breaker or fuse to trip, disconnecting the power and preventing electric shock. The NEC specifies the requirements for grounding electrical equipment. These requirements are designed to ensure that the grounding system is effective in protecting people and property from electrical hazards. There are several different methods of grounding electrical equipment. One common method is to use a 3-wire cord with a grounding plug. The grounding plug has a third prong that connects to the grounding conductor in the electrical outlet. Another method of grounding electrical equipment is to use a metal conduit. The metal conduit provides a continuous grounding path from the equipment to the grounding system. The grounding system should be designed and installed by a qualified electrician. A qualified electrician has the knowledge and experience to properly design and install a grounding system that will protect people and property from electrical hazards. It is important to hire a qualified electrician to perform any electrical work, including grounding. Attempting to perform electrical work without the proper training and experience can be dangerous and can lead to serious injury or death. The grounding system is an important part of any electrical system. A properly designed and installed grounding system will protect people and property from electrical hazards. It is important to have the grounding system inspected regularly by a qualified electrician to ensure that it is in good condition and is functioning properly. In summary, grounding the neutral is a critical aspect of electrical system safety and performance. It ensures voltage balance, provides a low impedance path for fault currents, and helps to protect people and equipment from electric shock. Regular inspection and maintenance of the grounding system are essential to ensure its continued effectiveness. Firstly, it's important to understand that the purpose of grounding the neutral conductor is not solely to balance the voltage from the transformer. Secondly, voltage balancing is one of the key benefits, but the primary goal is to provide a low impedance path for fault current to return to the source, allowing overcurrent protection devices such as circuit breakers or fuses to operate and clear the fault. Thirdly, the NEC, specifically Article 250, provides detailed requirements for grounding and bonding electrical systems. The neutral conductor is grounded at the service entrance and often at the transformer to establish a reference point and facilitate the flow of fault current. Fourthly, this grounding creates a bond between the electrical system and the earth, which helps to limit voltage rise during fault conditions and provides a path for unwanted currents to dissipate. Fifthly, the grounding electrode system, which typically includes ground rods, metal underground water pipes, and concrete encased electrodes, provides a connection to the earth. Sixthly, the size of the grounding conductors is determined by the size of the service entrance conductors, as specified in NEC Table 250.66. Seventhly, bonding refers to the connection of all non-current carrying metal parts of the electrical system to the grounding system. This ensures that all metal parts are at the same electrical potential, minimizing the risk of electric shock. Eighthly, the equipment grounding conductor, which runs with the circuit conductors, provides a path for fault current to return to the source from equipment such as appliances and tools. Ninthly, a ground fault circuit interrupter, or GFCI, is a device that detects ground faults and quickly interrupts the circuit, providing additional protection against electric shock. Tenthly, it is crucial to ensure that all electrical work is performed by a qualified electrician and that the electrical system complies with all applicable codes and standards. Incorrect grounding can create dangerous conditions, including electric shock and fire hazards. The concept of voltage balancing is related to the fact that the transformer on a pole typically provides a split-phase 120 volts/240 volts service. The center tap of the transformer secondary winding is grounded, creating the neutral conductor. The two hot legs each provide 120 volts relative to the neutral, and 240 volts between them. If the loads on the two hot legs are not balanced, current will flow in the neutral conductor. Grounding the neutral helps to minimize voltage imbalances and ensures that the voltage on each hot leg remains relatively stable. In addition to grounding at the service entrance, the NEC also requires the neutral to be grounded at the transformer serving the building. This is typically accomplished by connecting the neutral conductor to a grounding electrode at the transformer location. The grounding electrode is usually a ground rod or a metal underground water pipe. The purpose of grounding the neutral at the transformer is to provide a low impedance path for fault current to return to the source. This helps to ensure that overcurrent protection devices operate quickly and effectively in the event of a fault. The size of the grounding conductor at the transformer must be sufficient to carry the maximum fault current that could occur. The NEC specifies the minimum size of the grounding conductor based on the size of the transformer secondary conductors. In addition to grounding the neutral, it is also important to properly bond all metal enclosures and equipment to the grounding system. This helps to ensure that all metal parts are at the same electrical potential, minimizing the risk of electric shock. Bonding is typically accomplished by connecting the metal enclosures and equipment to the grounding conductor with bonding jumpers. The size of the bonding jumpers must be sufficient to carry the maximum fault current that could occur. The NEC specifies the minimum size of the bonding jumpers based on the size of the circuit conductors. Grounding and bonding are essential for the safe and reliable operation of electrical systems. It is important to ensure that all grounding and bonding connections are properly made and that the grounding system is properly maintained. Incorrect grounding and bonding can create dangerous conditions, including electric shock and fire hazards. In summary, the primary purpose of grounding the neutral is not solely to balance voltage, but rather to provide a low impedance path for fault current to return to the source. This allows overcurrent protection devices to operate and clear the fault, protecting people and equipment from electrical hazards. Voltage balancing is a beneficial side effect of grounding the neutral, but it is not the primary reason for doing so. The NEC provides detailed requirements for grounding and bonding electrical systems, and it is important to comply with these requirements to ensure the safety and reliability of the electrical system. The electrician is responsible for ensuring that the electrical system is properly grounded and bonded, and that all grounding and bonding connections are properly made. The homeowner is responsible for maintaining the grounding system and for ensuring that any electrical work is performed by a qualified electrician.